Мы переходим к следующему докладчику. Мне особенно приятно представить самого юного участника нашей конференции. Иван, он самый младший из всей семьи или из всего кластера, у которого голова — это Вадим Александрович Малышев. Вот он расскажет сегодня о работе, которую он сейчас делает с Андреем Замятиным. Ну, пожалуйста, Иван, вам слово.
Да, спасибо, Татьяна, за теплое представление. Так, ну мы, я так понимаю, на английский переходим, да?
Да, пожалуйста.
Хорошо. So, yes, like Tatiana said, my name is Ivan Krasnov, and I'm the last postgraduate student, Vadim Alexandrovich Malyshev, and it's a really honor to speak after such distinguished mathematicians. And of course, for me, really sad that I didn't work with Vadim Alexandrovich as much as most of you, but anyway, it was a big happy to know him and work with him until the very end. So today I'd like to tell you about the hitting probabilities for random walks in a street. This problem was originally stated by Vadim Alexandrovich, and now we continue working with Andrei Andreevich Zamyatin on this. So let's start. And let's consider the simplest case, which, how I said, Vadim Alexandrovich gave me. We will not consider this part a lot, but anyway, it's like an introduction. We'd like to consider the simple random walk with state space Z plus product by 0 and 1 and the following transition probabilities like you see here in the illustration. Further in this thesis, we will give more strict definitions, but here it will be enough. So if we are now in the point x1, for example, we can jump left with probability p sub minus, to the right p sub plus, and down p. And for another point, it's totally the same probabilities, jumps left, right, and to another point. We'd like to find the probability that a particle at point x1, for example, and x0, xi in general, will reach point 0, 0 earlier than the point 0, 1. And let's denote it like this symbol p, top index xy, and sub 0, 0.
Sorry, and what are the conditions on the left-hand side? What are вероятность t из 0,0? Какая она? Изначально координат.
If we are in the 0, 0 point, this is the probability is equal to 1. Sorry, I did a mistake. We want to go
okay.
0, 0. It doesn't matter because that's why I did this error.
Yeah. Okay.
So yeah, and in this simplest case, we can get the exact values for these hitting probabilities using generating functions. It's not a very hard task, but what is the interesting here and what I'd like to say maybe for potential discussion later or in the further questions, that this task can be interpreted in the language of the electric networks, which good describes in work Doyle and Snell. And the main idea that we can put some resistors on each edge between each vertices on our lattice, Z plus product 0, 1, and put some voltage at this point and, for example, 1 voltage here and 0 voltage here. And in this case, the voltages V of X inside this lattice will be the hitting probabilities itself. It can be shown really simple, and the main idea that transition probabilities here is pretty the same, that 1 divided by resistance of these resistors. It was a really short introduction, and let's go to the main part of topics and what we did. We improved and we tried to do some generalization and consider not Z plus product by 0, 1, but Z, full Z, multiplied by the finite set 0, 1, etc. n. So we consider the random walks in the strip, but strip is infinity for horizontal and finite for vertical. Let's denote Xi sub n is the pair Xi1 and Xi2n if the state of the chain L is the original chain at the time n. This chain at the discrete instance of time, how it's written here. And the transition probabilities are given as follows, and we will denote it P top index xy and subindex yj. J. What assumptions we want to hold? The first says that the first coordinate lower boundness, that means that probability is equal to 0 if x minus y greater than 1 model. For it's how lower boundness, we don't allow jump a very big distance. And the second one, that the first coordinate spatial homogeneity, it means that the probability of transition form of point xi to a point yj is independent of x. It means that you can see here. We use, yes, pretty the same condition like Vadim Alexandrovich and Mikhail Vasilyevich Menshikov considers in his books, articles, I think, and follows here. Then define the induced Markov chain, which we will denote L sub int as a finite state Markov chain with the state space 0 until n, and the transition probabilities P from E to G, Y to G, which is Q, we will denote. It means the idea that this is this transition probability is the sum from all possible probabilities jumps from point with coordinate I to all another. And also denote that P sub E is the stationary distribution of the induced Markov chain L int, and denote the mean jump M of I, that is expectation of this value of this statements. Finally, we define the induced drift vector M like product of mean jump by stationary distribution of the induced chain. It's not enough because we'd like to get some limit theorems, limit statements for these hidden probabilities, and one more chain which we should to consider here is an embedded Markov chain, which construction describes here. Again, we have some starting point x0, I0 from the original state of the chain L. And let's get some random moments of time tau and tau 2, tau x0 defined here, but the idea of definition tau 1, tau, etc., that this is the moment of time when horizontal coordinate decrease by 1 and 1 and 1 and 1, etc. So it means that tau k is mean that at this moment of time we will go from the original x0 by k steps left. We want to drift to the 0. So how it says here, tau x0 is the first moment of reaching 0. It means that C1n is equal to 0, where C1n is the first coordinate of 2, which describes our initial random walks, and this provided that C10 is equal to x0. So it's useful to note here that the distribution tau k plus 1 depends only on the value of C1 tau k. So this is the moment of when we jump to the k step slide at the moment tau k. Finally, we can define the hidden probabilities. Yeah, it's a good time. But first of all, let's suppose that induced drift vector m no greater than 0. It can be shown that the values tau k are finite with probability 1. And since we are interested in the probabilities of hitting the boundary, 0 boundary, consider some finite set A. This is pairs 0 I, so it's like a 0 intersection of my strip. And we can define the hidden probabilities as probabilities in which starting from point x0 I0 and the second coordinate C2 sub tau x0 is equal to y. Due to this equation holds, it means that we can here remove this condition and write it just with these statements. These are the probabilities of Markov chain L, our original Markov chain, arriving at state 0I in A. In A describes here earlier than any other state 0L, not in A, where L not equal to I. Finally, we define a finite state, again, embedded Markov chain. This Markov chain will be the chain at tau k moments of time. And this Markov chain is finite state Markov chain, again, with space 0 to n. And let's see to tau k. The tau k is the state of this embedded Markov chain at time tau k, like it was postulated in the previous slide. And the transition probabilities of my embedded chain is V I to J. So now we have the following chains. We have original Markov chain L with transition probabilities P. We have induced Markov chain L int with transition probabilities Q. And we have embedded Markov chain L embedded, LM, with transition probabilities Vij. But the difference between this embedded chain and the induced chain, that this chain at the moment of tau k. If we denote the stationary distribution of embedded Markov chain as nu sub I, we can prove the following lemma. So if m not greater than 0, then the hidden probabilities starting from point x0 I0 to and hit point 0 I is the sum of is the sum of the following product of transition probabilities in embedded Markov chain, where sum over all possible states, which is equal to V from I0 to I for X0 steps. Well, yeah, how it's right here. More interesting results which we had, that if again induced vector M no greater than 0 at x0 tends to infinity, the following statements holds. The hidden probabilities x starting from x0 I0 and hit 0 I converges to the corresponding stationary probability nu sub I of the embedded Markov chain and embedded. So you see it here. And furthermore, the convergence in this statement exponentially fast and uniform on I0. And also this is directly following from the previous point. For two states from from 0 to n, the difference between two hidden probabilities is have this asymptotic. It's good to note that in this case, which we described in the very beginning, of course, we have these converges, but how I said previously, on this very simple case, when we consider the random walk in the strip height 2, we can get the exact values for these hidden probabilities. Here we don't. Here we can't do it, but anyway, we try to do it anyway. But what we already done, that we had some asymptotics. The corollary here that the results it's true if instead of reaching separate point 0 I, we take the set, the finite set A sub P, where P is original state of the space of the state Markov chain, and here you see the result.
Эту речь по вероятность достичь множества А это же любое множество, что ли?
No, A is the subset of P.
Ну, P это вся вертикальный отрезок.
Yeah.
Так вероятность достичь его равна единице, мы у него попадем все равно, наверняка.
Но это же может быть не все множество.
Нет, пускай все множество, пускай все множество. Тогда будет единица. Что написано? HA, исходя из x0 и 0, это O большое от альфа в степени и 0. Но это же не может быть так. Если его будет единица, если это все множество. А справа что-то маленькое. Это что-то не то, не понимаю, что здесь написано.
Но если у нас А не все множество.
Ну, вся половина множества. Вся половина множества. Ну что, там будет где-то 1/2, да, или около того. А почему-то большое от альфа в степени и 0.
Ну, тут просто может быть, что, во-первых, снос будет, так сказать, направлен.
Какой снос? А это вся вертикаль.
Да,
это весь вертикальный отрезок.
Да,
к нему снос идет, к нему, к этому отрезку.
Здесь как бы, так сказать, возможен случай, когда снос будет направо.
Направо?
Да, да.
Направо вообще не попадем туда. Ну, с вероятностью там.
Ну, какая-то.
А где ты скажешь направо? Где ты скажешь, все я был налево, все я был снос налево?
Да, это не дописали. Ну, в смысле, это...
Что? Здесь теперь направо снос пошел, что ли?
Нет.
Что альфа тогда?
Здесь может быть любой M. Вот этот вектор. M-вектор может быть любым здесь.
Ну, почему стоит то большое от альфа в степени чего-то? Если снос влево, то слева будет единица. Мы пойдем в множество А, если весь отрезок. Наверняка. Да, аж любое множество из пи. Пускай это пи. Вот. Если это пи, то что слева стоит? Единица.
Нет, здесь есть некая, так сказать, неточность. Во-первых, здесь имеется в виду, что и блуждание рассматривается в бесконечной полосе.
Ну хорошо, и что?
И если А это есть просто какое-то конечное, так сказать, множество, то такая,
Сейчас, пи это
то
что?
такая
Пи это что такое пи в таком случае?
бесконечная, так сказать, полоса в обе стороны.
Ну и что, если А это вертикальный отрезок, а блуждание
Это
возврата, это наверняка впадет.
здесь, так сказать, имеется в виду не весь отрезок, а это может быть часть этого
Ну, теперь
отрезка.
половина отрезка все равно, почему будет?
Половина отрезка.
Коллеги, я очень извиняюсь, но у нас один докладчик не
Ну,
говорит
хорошо, ладно.
по-русски.
Что-то написано, я понять не могу. Почему эта вероятность, которая не мала, она
Вы
у большой от
переведите
чего-то?
дискуссию в английский.
So the question is the
Why the
following:
probability
why
which is not small initially, which can be arbitrarily close to 1, why it is all of something small? I don't understand.
So let's return to this question later, but I'd like to. So thank you very much, yes, for this remark. But let's continue and return to it later. Yeah, one more here, like technique when we can use here is using the green function, which, for example, describes in original book Spitzer. So here, our induced M vector isn't 0, and we can define the Green's function as describes here. So it's like an expected how many times we expect to be in the state x, y, starting from x0, I0. And if the initial state C0 of chain L, our original chain, is the finite set, is in the finite set A, we can define the distribution of the first return point, which denoted by R. R from 0, I0, return to 0, I, is the following probabilities. Where sigma A is the moment of first return into our set A, and then the distribution of the first hit point in A can be written as H from x0, I0 to 0, I, these probabilities. One more time, yes, we have distribution of the first return point R, and we have distribution of the first hit point, which we already had, but here we can rewrite it in other terms. And we had this result. If M isn't 0 and starting point x0, I0 in P, then the following equation holds. So we can express, we can probably express the hitting probability of Green's function and distribution of returns. How it's statement here, from x0, I0 to 0, I is equal to difference between Green function and sum of all Green function of sum over all states, Green function product by R. Yeah, and sorry. And if we can, using the result of Markov renewal theorem, where we have some limits statements for Green function, and what we want to do, we can prove the theorem related the hidden probability H and the stationary distribution nu sub I of the embedded Markov chain. to the stationary distribution P sub I of the induced Markov chain and induced drift vector and distribution of the first return point R from 0 to 0I. If and at x0 tends to infinity, the following convergence holds. So here we have our hidden probabilities, and here expression consists of induced vector, stationary distribution of induced chain, and returning distribution. And from the previous statement, from the theorem 3, we can consider the corollary that for the stationary distribution nu sub I of the embedded Markov chain, we can have this equation again consists of induced chains, stationary distribution, and distribution of return. So this is our references, and that's it. That I
Thank you.
in
You
time.
are perfect on time. Now we can continue discussion, or if there are questions, there are still a couple of minutes left.
Хотя бы либо какая-то ошибка, либо снос должен быть указан, снос в другую сторону, потому что because if you are on the net integer number, so you have a negative drift, then from any point on the right semi line, you can automatically appears in the origin with probability 1. Situation is the same. Here, situation is the same. You start in some point with coordinate I0, and you reach the point with coordinate 0 in origin. And this probability is the drift is negative or 0, then you reach this point with probability 1. Yes?
I suspect that maybe here not really hitting probabilities were considered. If you show us your previous theorem where alpha appeared first, I think that it was about here on the convergence. Maybe you meant that it is the difference.
I'm not sure, Tatiana. I should check it. Because yes, it's obviously that the probability shouldn't be very small. Yes,
I suspect it's not about, it is about rate of convergence, I believe. But rate of convergence to something, maybe you have to subtract these limitings. But okay, I think it will be definitely clarified later. Are there other questions? I would like to ask, did you use here also Lomonosov functions, or it is done entirely through different methods?
We will use it for more complex models when we will consider the random walks not in the finite strip like more like half and plane or quadrant.
Thank you.
So you study the operator, yes, you study the corresponding operator, yes? What is the method of proof here? Spectral?
Where? In the Lomonosov function or here?
Here, for this condition, Lomonosov function, yes, okay. Thank you.
May I ask one more question about this alpha? Do you have some
Exact values?
Or does it anyhow depend on the spectral property of the matrix for the transitions, for the probabilities or probability?
For here, for this case, no, but for the simplest case, sure, we have it. We have the exact expression for alpha. Expression, I try to remember this word during all of my topics.
Thank you.
But finally I do.
Thank you. If there are no more questions, we can go to next talk. Thank you, Ivan.